Researchers have designed numerous haptic controllers to render objects in virtual reality. However, many objects and interactions involve the coordinated use of both hands, and feedback between the hands is typically absent. We present Haptic Links, electromechanical connections which attach to standard VR controllers to enable intercontroller force feedback through variable stiffness actuation. In this clip, the user freely switches between dual pistols and a rifle held in both hands. Attached to their VR controllers is a haptic link. The haptic link allows for full 6 degrees of freedom motion while shooting the pistols. However, when using the rifle, the haptic link joining the controllers becomes rigidly locked, allowing the user to handle and aim the gun like a real two-handed weapon. We can also render variable stiffness along a continuous range. Here, as we pull back the drawstring on a virtual bow, the hinge between these controllers becomes increasingly stiff with distance, then relaxes upon firing. To appropriately position controllers to render a new object, we introduce an input method that we call summoning. That is, the user performs a gesture which moves their controllers into the proper position, enabling our system to haptically render the object through stiffening. Here, the user can summon either a car or a motorcycle by holding their hands in the shape of a steering wheel or handlebars. We designed 3 haptic links capable of rendering different types of intercontroller feedback. Each haptic link attaches to an existing, unmodified VR controller. The first link is a highly articulated ball and socket chain, with a cable threaded along its length. Linear actuators mounted to the controllers pull this cable tight, pressing each ball into the neighboring socket and globally stiffening the chain in its current configuration. Our second haptic link uses a hinge composed of several interleaved layers. By compressing these layers, we increase the friction between them and create a braking force. While the hinge controls the distance between the controllers, a ball joint beneath each controller enables rotation, which is locked using an actuated set screw. Our third haptic link uses the same ball joints but has a directionally selective brake on its hinge. Small servos disengage the pawls of 2 opposing ratchets, allowing for inward motion, outward motion, both, or none. This design enables us to render walls and surfaces, such as in this interaction, where inward motion is halted as the user grasps a virtual object with both hands. These last 2 designs allow us to constrain particular degrees of freedom while leaving others free, such as in this example, where the controllers can move together and apart in a locked orientation to render a trombone interaction. We envision a number of extensions for these devices, such as manually grounding one controller on the body or on another surface, to enable grounded force feedback interactions on the other controller. Our paper describes the design and implementation of our haptic links, as well as interaction techniques and scenarios leveraging their capabilities. Our user evaluation shows that users can perceive many two-handed objects or interactions as more realistic with haptic links than with typical unlinked VR controllers.